Okay, so today we talked about the curvature tensor. The curvature tensor is essentially built by the following construction. We have defined an affine connection. This gives us a covariant derivative. Okay, and then using this affine connection on the tangent bundle, there's a natural way, because it determines the parallel transport structure, you can use the essentially the parallel transport structure to create a difference quotient, which makes sense. And then you can take the dual map of these parallel transport isomorphisms to create a difference quotient, which you can then use to define, in the limit, you can define the covariant derivative of a one form. And then you can just extend this to to the covariant derivative of a tensor field by essentially constructing um, a parallel transport map on tensors using the parallel transport of a vector field, and the covector field, which are entirely determined by just the linear connection on the tangent bundle. So once you have this parallel transport structure, again, you can form your difference quotient and essentially take a tensor field at a take a curve gamma which aligns with the vector field x that you want to differentiate along the direction of, and then take a tensor field at gamma of t, parallel transport it back to gamma of 0, and then take the difference between that and the value of the tensor field at gamma of 0 divided by t, take the limit as t goes to 0, and that gives you your covariant derivative in the direction of gamma prime of 0 equals x of your tensor field. Okay, that's determined entirely by the linear connection. And so, but the point is that, in fact, if you look at the tensor algebra, okay, if you look at the algebra of these tensor fields, well, it's a graded algebra, right? The grade is just the rank of the tensor, and the algebraic structure the multiplication structure is given by the tensor product. Okay, we showed that the linear connection is compatible with this algebraic structure in the sense that it obeys the Leibniz rule with the tensor product, namely the nabla of x tensor y, or t tensor s, I guess we should use for tensor fields. Nabla of t tensor s is equal to nabla t tensor s plus t tensor nabla s. Okay, it's also commutes with the contraction mappings. Okay, but the important thing, so the fact that it commutes with the contraction mappings is just a nice fact, an important fact. Okay, but doesn't make it a derivation on the algebra. It's literally just a derivation because it satisfies this product rule. Okay, and so now that we know that it's a derivation, we can look at, okay, the set of derivations of this graded algebra of tensor fields. What are the set of derivations? Look at this more broad set of derivations. So for every vector field, I should explain actually. So nabla itself is not the derivation. It's nabla x for any vector field x, right? Nabla x. I shouldn't have said nabla of t tensor s. It should be nabla x of t tensor s is equal to nabla x t tensor s plus t tensor nabla x s. Okay. So we get a derivation for every vector field x that determines a covariant derivative in that direction, and that will give us a derivation. Okay. So this whole family of derivations, which are given by a single affine connection on the tangent bundle, which gets extended to the tensor bundle. Okay. So we have this whole family of derivations on this graded algebra of tensor fields. And notice that, in fact, there's a map which takes a vector field to a derivation, namely takes x to the derivation nabla x. Okay, but the set of smooth vector fields x, the set of smooth vector fields that we're mapping into the derivations, actually has a Lie algebra structure given by the Lie bracket of the vector fields. Okay, and so the set of derivations also has a Lie bracket structure. It has a Lie algebra structure also given by the commutator. Okay, you take the commutator of two derivations, you again have a derivation. Okay, so there's a Lie algebra structure on the set of derivations given by the commutator. Okay, and it turns out that, first of all, the Lie derivative, okay, the Lie derivative is a derivation. Okay, and it turns out that the Lie derivative is not just a derivation, but if you look at like the Jacobi identity, you can derive that the Lie derivative is actually a Lie algebra homomorphism from the Lie algebra of smooth vector fields to the Lie algebra of derivations. Okay, and the reason basically is that the Lie derivative in the direction bracket xy is equal to Lie derivative in the direction x composed with the Lie derivative in the direction y minus the Lie derivative in the direction y composed with the Lie derivative in the direction x. So the Lie derivative is a Lie algebra homomorphism from the set of smooth vector fields to the set of derivations on these tensor fields. Okay. Now, remember the Lie derivative is given by essentially looking at the flow. So if I take the Lie derivative in the direction x of some tensor field, I basically look at the flow of that vector field x, and then I pull back. So instead of using any parallel transport structure to pull back the tensor field to the original point, I just pull back along the flow of the vector field x. Okay, so that's the Lie derivative, and it's this Lie algebra homomorphism. But the like the map x to the Lie derivative in the direction x, the map which sends a vector field to the Lie derivative in the direction of that vector field, is a Lie algebra homomorphism. Again, sorry to repeat this so many times, from the Lie algebra of smooth vector fields equipped with a bracket to the Lie algebra of derivations equipped with the commutator. Okay. But we can ask the same question for the covariant derivative. So we have a map which sends a vector field to the covariant derivative in the direction of that vector field. X gets sent to nabla x. When is that map a Lie algebra homomorphism? Well, in general, it's not, and because it turns out that right, in general, this map is not a Lie algebra homomorphism, and somehow the failure of this map to be a Lie algebra homomorphism is somehow related to the curvature of the manifold. Okay, so the curvature tensor is defined as essentially the failure of this covariant derivative map to be a Lie algebra homomorphism. So namely, if we take the curvature tensor R of xy evaluated on a vector field z, this is going to be nabla x, nabla y, minus nabla y, nabla x, minus nabla bracket xy, all applied to the vector field z. Okay, and so yeah, so the Riemann curvature tensor it's considered a one, or not a Riemann curvature tensor, just the curvature tensor in this case. The curvature tensor, as we've just defined it, is a map which sends a vector field z to the vector field nabla x, nabla y, minus nabla y, nabla x, minus nabla bracket xy, all evaluated on z. So it's a map which takes in three vector fields, namely x, y, and z, and it outputs another vector field w, okay? So we can really view this as, if we compose this with a one form, omega, we can view this as a 1, 1, 3 tensor. So it inputs one covector field, three vector fields, okay, such that r of omega x, y, z is equal to omega of r of x, y hit on z. So with parentheses, it's omega, start parentheses, r, start parentheses, x comma y, end parentheses, z, end parentheses, okay? And so it's a 1-3 tensor. It's a 1-3 tensor field. You can prove that it is C infinity M linear in all of the components, in every component, okay? So in the components, namely x, y, and z. So that means that r of fx comma y z is equal to r of x comma fy z is equal to r of xy fz is equal to f r of xyz, okay? So when I say r of xyz, I mean r of x comma y end parentheses acting on z, okay? The z has a fundamentally different role. It's kind of, there's this derivation operator, namely this derivation operator, which is nabla x nabla y minus nabla y nabla x minus nabla x bracket y, or bracket xy. That is a derivation. That derivation is acting on z, okay? And it's measuring the failure, again, the failure of this map x sent to nabla x to be a Lie algebra homomorphism, okay? Now, geometrically, what does this have to do with curvature? It's not so obvious. And the answer is, we're going to talk about that later, because I don't fully understand the connection between the algebra and the geometry yet, okay? But there is a notion of, you parallel transport a vector along a loop, okay? And you measure the failure of, like, essentially the failure of the vector transported along this loop, or I guess along a quadrilateral spanned but locally by x and y, okay? You basically look at the flows of x and y, you form a parallel pipette, you parallel transport a vector through this, and you look at the failure of that vector to return to its initial position, okay? So there's something there, and I might have explained that wrong, because I haven't fully delved into that. We're going to get to that later, but not in this lecture, because the author, Professor Zuoqin Wang, these are his lecture notes, lecture 7, left it as a term project to the students. But I'm aware that many other textbooks cover this topic, so I'm going to be looking into this topic in more depth, but at a later time. However, we can talk about we can talk about this curvature tensor some more. So we could talk about some of the algebraic properties. Okay, so there's this interesting identity, and blanking on the title of the identity, but essentially you can show that if you look at this iterated map nabla, so remember we looked at nabla as this map to define the Hessian. We looked at nabla as a map which sends an RS tensor field to an RS plus 1 tensor field, where the final input vector field, so like nabla t of, if T is an RS tensor field, nabla T is an RS plus 1 tensor field, where the final input vector field goes into the covariant derivative. So nabla T of dot 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 comma x is equal to, by definition, nabla x T of dot dot dot. Okay? So in doing this, you can view nabla, basically, you can iterate nabla. You can iterate just this nabla operator. Okay? And if you iterate it twice, you get nabla squared. You apply that to a function, you get what's called the Hessian of that function. And remember that the Hessian of a function, a 0, 0 tensor, that Hessian is a 0, 2 tensor, and requiring that tensor to be symmetric, requiring the Hessian of a function to be symmetric for all functions on your Riemannian manifold, is equivalent to setting the torsion tensor T of xy, which is equal to nabla xy minus nabla yx minus bracket xy. Okay, so T of xy is equal to nabla xy minus nabla yx minus bracket xy. It's equivalent to setting that tensor equal to 0. Okay, and you can just work out the computation nabla squared f of xy and find that nabla squared f of xy is nabla y applied to nabla t dot 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 x, which is going to be, by definition, you're going to have nabla y. So you're going to have y. So you're going to have nabla y applied to the evaluated tensor. So that's just nabla xf. So that's just yxf. Okay, minus the tensor nabla t evaluated on, or nabla f, I guess, evaluated on nabla yx. So that's going to give you just nabla subscript nabla yx of f, which is just nabla yxf. Okay, and so, right, so we get, that's, yeah, that's nabla squared f of xy. If you look at nabla squared f of yx, you're going to get xy, or I think you're going to get, yeah, xy f minus nabla xy f. And then if you subtract those two, you're going to get nabla xy minus nabla yx minus bracket xy applied to f, which is your torsion tensor. Okay. So, anyways, going back to this discussion, the torsion tensor measures the failure of the Hessian of a function to be symmetric. But let's look at, if we look at, assume now that our connection is torsion free. Assume that our connection is torsion free. Okay. And now let's look at the Hessian, not the Hessian, but the nabla squared operator applied to an arbitrary tensor field, not just a function. So we know that since we're in a torsion-free, we have a torsion-free connection, the Hessian of a function is symmetric. Okay, so if we look at the nabla squared applied to a 0, 0 tensor, and we look at that, and we kind of look at the symmetry of the final two components, they're going to be symmetric. We can measure the difference of on it this kind of failure of the nabla squared operator to be symmetric in the final two components. We can measure that failure for an arbitrary tensor field. It turns out it's not in general symmetric. It's not in general symmetric. Okay, even if the Hessian of a function is, right, because we're torsion free in general, this And this is called the Ricci identity, by the way. Okay, but in general, this Nabla squared operator is not going to be symmetric in the final two components when it's acting on tensor field. Okay, so it turns out that if you take a tensor field and you look at tensor field T, let's say, you look at Nabla squared T of dot 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 comma x comma y minus Nabla squared T of dot 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 comma y comma x. You look at that difference, it's precisely equal to r of xy acting on T. All right, it's precisely equal to r of xy acting on T. So that is called the Ricci identity. The Ricci identity. What it says is that the Riemannian curvature tensor somehow measures the failure of this Nabla squared operator to commute in the final two entries when acting on an arbitrary tensor field. Okay? All right, and it's a nice algebraic exercise to try and prove that, but I think it's somewhat involved. I don't remember how involved. Okay, so then the other thing we could talk about are some symmetries of the Riemannian curvature tensor. So it turns out it's antisymmetric in, so r of xy, going back to r of xy is antisymmetric in x and y, okay? So r of xy z is equal to negative r of y x z, okay? That's just by definition, all right? So, yeah, so it's antisymmetric. And if you look at the coordinate form, okay, so, oh yeah, let's talk about coordinate forms, and we're going to talk about these symmetry laws and coordinates. So, the coordinate form of the curvature tensor, okay? You take coordinates, remember, it's a 1-3 tensor. So it takes in it eats one covector field and eats three vector fields. So that means we're going to have something in the form r subscript ijk superscript l dx superscript I tensor dx superscript j tensor dx superscript k tensor partial subscript L. Okay? So that's the component form. It's a 1-3 tensor. Okay? It's got 3 lower indices, 1 upper indice. Because again, it's going to be eating 3 vector fields and 1 covector field. Okay? So again, that's R subscript ijk superscript L dx superscript I tensor dx superscript j tensor dx superscript k tensor partial subscript L. Okay, that's the coordinate form of the Riemannian, not the Riemannian, just the curvature tensor. The Riemannian curvature tensor, I believe, is when we lower the indice, but we'll get to that next lecture. Okay, but let's just say it's very closely related to the Riemannian curvature tensor. Okay, very close. Okay. It's pretty much the same thing. I mean, people will call this the Riemannian curvature tensor, and you probably are correct to call it the Riemannian curvature tensor because that is probably the correct name for it, anyways. Okay. But okay, so looking back, what does the antisymmetry mean in coordinates? It means that it's antisymmetric in the first 2 indices. So r subscript I j k superscript L is equal to negative r j I k superscript L. All right. Now we have a couple more algebraic identities. So we have the cyclic symmetry, okay? So we have r of xyz plus r of zxy plus r of yzx is equal to 0, right? And the proof of that essentially uses the torsion-free, hinges on the fact that it's torsion-free, and then uses the Jacobi identity for the vector fields, right? So the proof of these results are like algebraic proofs that just unpack the definitions and do the right algebraic tricks, invoke the right symmetries. Okay. So it is good to review these algebraic proofs, but I'm not going to do so in this lecture. I'm just going to state the identities. Okay. So what does that mean for the coordinate form? We have that if you sum Rijk superscript L, where I, J, and K are subscripts, if you sum that over the cyclic permutations of I, J, and K, you get 0. Okay, so R subscript I, J, K superscript L plus R, K, I, J superscript L plus R, J, K, I superscript L is equal to 0. All right. And then, so that's what's called the first Bianchi identity. And then the second symmetry is called the second Bianchi identity. And this has to do with the derivative of the curvature tensor, okay? So if you take nabla R, okay? Nabla R is all of a sudden has one more input, namely one more vector field input in the final component, obviously, okay? So nabla R, if R is a 1,3 tensor, nabla R is a 1,4 tensor, okay? Nabla R is a 1,4 tensor. Now, if you sum, so the key identity is that nabla R of X, Y, Z, W let's use slightly different ordering here, okay? Or yeah, no, this is fine, okay? So nabla R of X, Y, Z, W cyclically summed over X, Y, W is 0, okay? So nabla R cyclically summed over nabla R of X, Y, Z, W cyclically summed over X, Y, W is equal to 0. I believe that that's correct. Let me double check that though. Yeah, let me quickly double check that. Oh, wrong book. Okay, yeah, I think I stated it correctly. So in this case, okay, I'm just gonna show you how they write it, but this is just yeah, I said it correct. Yeah, 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 I said it correct. And then in coordinates, check out this. So in coordinates, we have this partial, and we can take the covariant derivative with respect to one of these coordinate vector fields, and we're going to write that in the following way. So look at the notation here. We take the semicolon, and use the semicolon lower indice n to denote the direction of this covariant derivative. Okay, that's an important notation. Okay, so then the second Bianchi identity can be written as this. You see, the third index is fixed. The k and the l indices are fixed. And we do a cyclic summation over I, j, and n, and we get 0. All right. Now I'm just going to go ahead and quickly just show you the lecture notes, and you can pause the video and just review the formulas or anything that you want to review. All right, so here's first page. Maybe I should do it like this. All right, so here we have this, what we were talking about before. We have this first lemma. Oh, yeah, okay, this is actually a nice lemma I forgot to mention. So this tells us that basically, if you look at r of xy applied to a 1 form, it's just negative, evaluated on a vector field, it's just negative that 1 form r of xy applied to z. Okay, so this means that since, listen to this paragraph, since the graded tensor algebra is generated by smooth functions, vector fields, and 1 forms, together with the fact that r of xy is again a derivation, okay, so r of xy is a derivation, since we can write this r of xy applied to a 1 form just in terms of basically the r of xy applied to the vector field, okay, we only need to study r of xy and vector fields, okay, because of that. So that's critical. All right. Now, okay, so again, we have this as we discussed. Okay, so R is truly a tensor of type 1, 3. Let's see, here's an example. Okay, we talked a little bit. Okay, so we didn't talk about flatness. Flatness is essentially locally. You can find a local isometry to Rn equipped with the Euclidean metric. So you can find a local isometry to Rn equipped with the Euclidean metric, and this is only true if the curvature tensor vanishes identically. Okay, if the curvature tensor vanishes identically, that's if and only if your manifold admits a local flat frame. Namely, you can find a set of vector fields on a neighborhood such that they form a frame. They frame the tangent bundle of the manifold, and their covariant derivative vanishes in all directions. Okay, so they're basically fully parallel. Okay, and yeah, their covariant derivative vanishes in all directions. I don't think that's just. I think that that's stronger than being fully parallel. Or yeah, no. That is just being parallel. Okay, so you can find this local flat frame everywhere. This is the key proposition. Then the curvature tensor is identically 0 if and only if your manifold equipped with this linear connection admits a local flat frame everywhere. Okay, and then it's going to be locally isometric to Rn with the Euclidean metric if it admits this local flat frame everywhere. Okay, we have the Ricci identity. So this is the Ricci identity that I mentioned here. Okay, where this nabla squared yx is by definition, just for simplicity, you can see the definition here. It's just the final two entries are x and y respectively. Okay, so we have this identity, and then we have the first Bianchi identity. Okay, so the first Bianchi identity is here. This is the cyclic permutations. Okay, we have the anti-symmetry here. We have the cyclic permutations. Here's the cyclic permutations in coordinate form. And then we have the second Bianchi identity. So this is different lettering than what I used in my lettering. You can see this third component is fixed. This W is fixed here. And you're cyclically permuting over the first, second, and fourth entries of nabla are, basically. Okay, and this is written in local coordinates. I already showed you that. And then also, if you write these cyclic sums, then we have the following identities. Okay, just in terms of the cyclic sums. Okay, all right. So have a really nice day.